So this design has come from a customer called Nomad. They are designing a battery energy storage system. Battery energy storage system, or BESS, is basically a container full of battery packs to provide electricity in remote places instead of a diesel generator. So you use these devices, these BESS, in an electrical network that help you to fluctuate the loss of power for renewable energy. When you don't have sun, when you don't have wind, you can rely on the batteries and then charge them back when you have renewable energy source. But there is a big challenge here. There is the weight. So we do a lot of structural simulation, of course, the lifting crane, lifting forklift. We do transportation load cases from standard. We do seismic simulation with linear dynamics. We even do sometimes blast simulation, simulating a thermal runaway and the ignition of gases inside to make sure the container is strong enough to contain the blast. But here, indeed, to prevent a blast, we have to cool the battery down. There is a very big thermal challenges to make sure the temperature is not crazy high. So they ask us to design a ducting system to provide cold air from an HVAC. So here a big HVAC is going. How to provide the cold air from the HVAC and distribute it evenly across 204 batteries inside the enclosure. It's not an easy challenge. So here what you see are the battery racks. You have 12 racks and each rack has 17 batteries piled up. So we are going to use the algorithm to help us to find the most suitable design. So we first have to think of a concept, and we have this baseline concept. So here, a view from the top. If you imagine, picture the HVAC here, we would blow the cold air towards two kind of inverted triangular shape. And on the side of this triangular shape, we're going to position holes to distribute the cold air towards the 6 racks on each side. But by creating that CAD with parameters, we are able to not only generate one, but generate dozens or hundreds, playing with the angle of that V shape, the entry width of that V shape, the size of each hole, the offset between the hole center and the center line of the batteries. And by having just 10 parameters, we are able to generate hundreds of design iteration. Then we define the scenario. So in the fluid scenario, so the cold air comes from the HVAC provided by a blower. A blower has a fan curve to follow. So it's too simple to just choose the volume flow from the HVAC, because the volume flow you get from the HVAC will depend on the fluid obstruction of your duct. So we want to make sure that we will create a duct that is the least obstructive, so we have the most powerful volume flow out of the HVAC blower. So the input is not a volumetric flow, the input is the fan curve. So it will read the pressure loss out of the simulation and tell you what volume flow you are able to provide. Then normally it's a closed loop, but here we want to simplify things a little bit. So the flow gets in the HVAC, and each batteries has an internal fan sucking air in. That is considered as the outlet boundaries of our fluid domain. As the fan is sucking in air, we have a negative pressure to mimic that. We use a half symmetry domain again to simplify a little bit the simulation. The fluid domain is meshed quite efficiently using the volumetric X dominant mesh from the platform. And we are able to create refinement boxes at the key location for a total of nearly 2.3 million elements. And we use the same approach you're now familiar with the design of experiment driving a physics simulation, which is now no longer finite element analysis, but CFD analysis. The input, of course, are the design variables, and the output we want to focus are the volume flow from the HVAC to make sure we maximize the volume flow from the HVAC And we are measuring the volume flow getting inside each of the batteries to make sure that the difference between the maximum and the minimum is reduced. So we will have a more homogenized flow, a better distributed flow across each of the batteries. And we were able in 48 hours of compute time to generate 54 design iteration. Here again, you see that each point is one design iteration result. Here on the x-axis is the run ID, so number 1 to number 68. Few of them failed because of the CAD reconstruction, but still you have successfully 54 design. On the y-axis, we have the volume flow from the HVAC. And you could see the span, the efficiency of that study. The most obstructive flow was generating a flow out of the HVAC of slightly above 4,000 meter cube per hour. But the least obstructive design was generating flow up to nearly 6,700 meter cube per hour. So it's not double, but it's a big improvement. So that shows that it's very sensitive. The flow is very sensitive from the design of the air duct. Again, to make the data talk, you're able to get this correlation map that help you to find out the most relevant design parameters for your output. So if we focus on the volume flow from the HVAC, we learned that the higher the number, the higher the sensitivity. So here we learned that the angle, the interior angle of the V shape, that number was the most impactful if we want to maximize the volume flow. So that's very interesting. And for example, the offset of the holes has no effect or nearly no effect on the volumetric flow. So that's very interesting. We learned also that the homogeneity of the air was mostly driven by the width of the entry of the V-duct. So you learn, not only you find the best design, but you learn a lot about the sensitivity once again. Finally, you can select few of them, select it as your best design and do a trade-off study to find the best design. And finally, we compare with the concept and we managed to increase the volume flow by 25% while improving the flow distribution by 10%, 8% exactly. And all of that took us 1.5 weeks of engineer time because of this algorithm that was doing the job for us. And this is the final duct. And as an engineer, I really like the design because no one can guess why the holes are from a different shape, but the simulation knows. And I saw that design in the manufacturing line, and I've been told that it's raising a lot of questions, but it's very cool design.
Wonderful, thank you, Benjamin. And we actually have a question as well from Matthew. I don't know if you can see it, but it says, when you submit this job for the dimension iterations, is it all in the cloud and are all result ODB files still stored there? Or can you do this locally on a prem cluster?
Yeah, it's a good question. You can do both. You can do cloud, you can do on-prem calculation, depending on the installation settings that you have. But you have the option not to store all the ODB file, of course. Otherwise, it's a lot of data. So if you want, you can store all results. But what I recommend is not to store them. So you have this kind of light summary of results that you can consult, find the trade-off, and then yes, you can regenerate the design iteration to have the full result if you want to consult the entirety of your result file. But it's a lot of data that you're going to generate. And this is the power of this algorithm, that by specifying the output in advance, you don't have to open the full ODB. But both compute power are available, cloud and on-prem cluster.